In this video, we will discuss how to construct a computational graph. And we will, first of all, we will introduce what is the computational graph. Okay, suppose we have the model here. So for the model, we have some input and it will output something out. And the input might be, for example, for computer vision, the input might be an image. And in the model, we may using some kind of the convolution or linear layer or whatever. We will provide a way to define the model here. And then, typically, we will not execute this model directly here. Instead, we construct a computational graph to calculate the model, to evaluate the model. The reason is that we need to do the backpropagation later, so that if we don't control the computational graph, we need to implement the backpropagation by hand. This will be something very difficult. In our exercise 1, we will provide an example for you to write the backpropagation by hand. You will see that this is something really difficult and very easy to make mistake. So in most of the deep learning framework, we will construct a computational graph and you use something called automatic differentiation to do the backpropagation automatically. So the designer of the model, we don't really need to write any code for the backpropagation. Everything in the backpropagation is implemented in the framework. We only need to implement the backward function in the functions. And if we will always using the functions provided by the framework, we actually do not need to write any code for the backpropagation. So in the rest of the video, I will explain how to construct the computational graph and how can we implement the backpropagation. Okay, so the other reason that we want to compose the computational graph is that our code is written in Python. So, but if we evaluate the models in pure Python, the performance will not be acceptable. So typically, we will construct a computational graph, and the framework will actually convert the computational graph into something which can be implemented in C or C++, or even it will be implemented by using the hardware instruction provided by the GPU. For the NVIDIA, it will be the CUDA. So eventually, even though we write the program in Python, but actually the Python program will be converted to the computational graph, and the computational graph will be converted to some basic functional blocks, which is written in C or C++ or in GPU, so that the performance will not be limited by the Python interpreter. So this is the reason we need to have the computational graph in here. Okay, so let's see what's the computational graph. Suppose we have a very simple expression here, the a plus b multiply c and multiply 3. So let's see how we can use in the computational graph to evaluate this expression. So first of all, we need to define the variable, the a, b, and the c. So we put a circle to indicate that this is a variable in the computational graph. Then according to the Python expression here, the Python interpreter know that we need to do the B multiply C first and add the result to the A. So in the computational graph, we will put a function multiply here. All the function in the computational graph will be a square here. Okay, so the B and the C are input of the multiply function, and this function will output a variable U here. The U is not in the expression, in the Python expression. It is an intermediate temporary variable which is required to evaluate the whole expression. And the U will be added to the A. So A plus B multiply C will become the U. So A plus U. So we put an add function here. And the input of the add function is A and the U, which is B multiply C. And this function will output a variable V here. So that's the entire expression here. And then we need to multiply it by 3. So we just create a variable called 3, and the 3 and the V will be the input of the multiply here, and we will input the variable and assign it to the F here. So this is the entire computational graph for this expression. So suppose that the value of A, B, C is 2, 3, 4. So let's see how we can evaluate this computational graph. Actually, it's quite easy. So we just as we know how to do the math before, we just multiply B and C together to produce the U, and the U will plus the A. So the 2 plus 12 is 14, and the 14 multiplied 3 is 42 here. So this is how we do the evaluation of the computational graph. Then we need a gradient. We know that in order to implement the gradient descent, we need to evaluate the gradient for every variable in the computational graph. And first of all, I will introduce something called numerical differentiation. So by using the numerical differentiation, we do not need to implement anything. We just using the computational graph to get the differentiation of all variable. How we can do that? This is quite easy. We just found the definition of the differentiation. For example, if we want to have something, the df over dA, it's the gradient of f against A. We just increase the variable to be something a little bit higher than that. For example, for the V here, we just increase it from 14 to the 14.001. Okay, so and then we evaluated the computational graph again, so we know that the f will become the 42.001.003 here. So that the df is from 42 to 42.003. So the df will be the 0.003 here, and the dv is from 14 to 14.001. So it will become the 0.001 here, and the differentiation of the df over dv, the gradient of f against the v, will be 3. Okay, so we can do the same thing for any variable in the computational graph. Let's try to do it for the A as well. So when we increase the value of A from 2 to 2.001, and then this will become the 14.001, and the f will become to 42.003. So the df over dA will be 3 again. And then we can try something more difficult. We want to do the df over db. So we increase the value of b from 3 to 3.001. And then this will become 8. The multiplied by 4, it will become the 12.004. And then, okay, so we know the df will be 0.012. So it means that the df over db will be 0.012 and the 0.001, which will be 12 here. Okay. But that's we can do the numerical differentiation by that way. But there's the other way to get the gradient of every variables. For example, here, if we want to evaluate df over dv here, we know that the v is the input of the multiply function here, and the f is the output of the function, so that we can using the chain rule to convert the df over dv become df over df multiply df over dv. So we just insert the output variable to convert this expression to this one. This look trivial because the df over df is 1, so the left side will be equal to the right side. Okay, but we can apply the same rule for other variables as well. For example, the df over dA here, a is the input of the function add here, and the v is the output of the function add, so that we can insert the v into the gradient here. So the df over dA will become df over dv and the dv over dA. So this time it's not trivial. For the first term here, we need to look at it very carefully. For the first term here, it actually the gradient of the output function. So it's a gradient of a v here, and so that we can assume that this gradient has been decided before. So whenever we calculate the gradient, we can catch the result, so that in the future, if we other variables need to reuse this gradient, we can use the value without evaluate the gradient again. Okay, so for the df over dv, this is something called the upstream gradient. Why is it called upstream? We will know that later. Because now we need to do that will related to the back propagation. So back propagation means that we will calculate the gradient from the end of the graph toward the beginning of the graph. Okay, and the second term, it will be always the output over input. Since the v will be the output of the function here. Okay, and the a is the input of the function. So the second term will always be the gradient or the differentiation of the function itself. So we can easily define the way we calculate this function in this differentiation inside this function. Okay, so it will be fixed in the function no matter what's the input or output of the function. This differentiation could be decided mathematically in a closed format, so that we can write this one as a function. Actually, this one will be calculated by the backward function of the add function. Okay, but here we just ignore the implementation for now. We just concentrate at the computational graph itself. So the dv of the dA, since v is the result of this function, so we can replace the v with the function itself. So the v will be equal to a plus u. So it will be a plus u here, and then this will become 1. So the df of dA will be the df of dv here. And we don't really need to do the df of dv here since it has been decided before in the previous state. So we're just using the cached value to do the job. Actually, we don't really need to look at the v directly because this value, the df dv, will be passed into the function, into a backward function in the backpropagation algorithm. We will discuss that later. But for now, we just need to know how we can, using the chain rule, to decide the differentiation of or the gradient of every variable in the system. Okay, so all of this will be done in a backward pace. So it means that in the first step, we will do the df of dv. So the df of dv, so f will be equal to 3 multiplied v. So it will d3 multiplied v over dv. So this will be always 3 here. Okay. So the gradient of the v will be always 3. Okay. And then let's do something more difficult. For example, if we want to know what's the df of du here, again, we're using the same rules. The v is the output of the function plus here, so we just insert the v into the differentiation of the f against the u. So it will become the df over dv multiplied dv over du. And for this one, we know the value already is 3 here. And for the second one, is actually the differentiation of the function itself. So just like we discussed before, the v will be the a plus u here, and this term will be 1. So the value will be 3. Okay, so we know that the df of dv will be 3 here. And then we can move toward the beginning of the graph. So we just try to decide what's the df over db for this variables. Since this is the input of this function and the u is the output of this function, so we're just using the u in chain rules to decompose this differentiation into 2 terms. The first one is df over du, the second one is du over db. So du over db, we can just replace the u with b multiplied c here, and this differentiation will be the c. And the df of du, we have calculated this before, so it will be 3. So it will be 3 multiplied c. And we know that the value of c is 4 here. So we know that the differentiation will be 12. Okay, so let's repeat it again. We will calculate the differential of every function against the f here. So the first is df over df, which will be 1. So we will just assign it to be 1. And then we will go backwards in this computational graph. So the f is the output of the function here. So we just going back to get the function. And then we know that this function has 2 inputs here. So we just call the backward function of all the inputs and try to decide the gradient of those inputs. So in here, we want the v is the input of this function, so we just calculate the df of dv here. And also we don't show the result of the df over this variable. This look like a constant, but as we will see soon, this will not be a constant. Typically, we will make this as a variable. So you will become the parameter of the model. We'll discuss that later. But for now, we can using a recursive way to call the backward function of the function of y. Since after we decide the value of df of dv to be the 3, so that we can call the backward function of this addition add cut object here, and then we pass the df of dv into this function, so that this function will know that the upstream gradient, which is the gradient df of dv here, will be 3. And this function know that it has 2 input, so it will actually try to decide the df of dA or df of du here. For example, it will call the df of du here and pass this value to the backward function of and then since the dv of du is the v here, so we inside the backward function of the add here, it know that the dv over du will be 1. So you just multiply 3 with 1 to get the gradient of the u here. And you just set the gradient of u to be 3. So the gradient of u will be 3. And then we can just go backward. But since the a is the is the input of the whole expression here, so we just stop. But for the u is the output of this function. So again, we will just call the backward function of the multiply function here, and paste the df of du, which is 3, into this function, and this function will do the same thing again. Okay, so you will see that why this procedure is called the backpropagation. Since we will start from the end of the computational graph, which will be some functions, and we will try to decide the gradient of f against every variable in the computational graph, so that we can know that if we change the value of u, how much the f will be changed. If we change the value of v, how much the f will be changed. So that because our purpose, typically our purpose is that we want to adjust those parameters to let f become some specific number, which will be the ground truth or the label of our data set. I will discuss that later. But for now, you only need to understand that why we need to study it from the end of computational graph toward the beginning of the computational graph, because this will save a lot of computational effort. Since when we want to decide the df of du, we need to decide the value of df of dv first. Okay, so we need to do the df of dv before the df of du. And then again, the same thing, if we want to calculate the df of db here, we need to have the value of df of du first. So this need to be done before the b. So this is the gradient of the variable of a function is always depend on the output of the function. Okay, so this means that we need to start from the end toward the beginning, so that when we want to decide a gradient of some variables of a function, the output of the function, the gradient of output of the function has been decided already, so that we can use the value directly. Okay, so this is called the automatic differentiation of the computational graph. Since that we do not need to write the df of du by using the chain rule to get the whole formula to calculate it. If you need to do that, it will become something very difficult and very easy to make a mistake. And actually, in the early day of a neural network, people need to write the equation by hand, write the differentiation formula manually. So it's a procedure very difficult and very easy to make a mistake. As I said before, we will provide the exercise one for you to try how difficult it is and why we need the backpropagation algorithm. We will about to discuss. Okay, so let's discuss another concept called loss function. The formula we use here, it doesn't really make too much sense to implement it by using the computational graph. Actually, typically, for any of the models here, so if you suppose f is a model, so any of models here, we need to define a loss function, which let us has a capability to adjust the parameters in the model, so that the model will always output a correct answer for our input, just as we has discussed before. For the models, you need to make a prediction based on the input values, and a good model will make a prediction which is very close to the answers. So in here, we just add a loss function here. So supposedly we're using the mean square as our loss function. I won't go into the detail about what's the loss function we need to use here. You just need to know we are using the mean square, the square function as our loss function here. We will go back to discuss what's the loss function we need to use for any kind of a situation, to all kind of situation later. And in here, since we're using the square as the loss function, and the 44 here actually is a ground truth. Okay, so this is the answers we want to have from our models. Okay, so the yellow, the object in yellow is actually the input of the function. And then you will see that I label the 3 here as green. Okay, and the green here is actually the parameters in our models. So why it's called parameters? This look like a constant. Let's explain it. So for those 3, the u, v, f, we cannot change those variables. Why? Because those things are decided by its input. Okay, so we cannot just although we know when we do the menu differentiation, we say that we change the u to something a little bit higher than that, but actually we cannot do that. That's just for numerical differentiation. In practice, the value of u is always decided by the function from the input value here. So if the b is 3, c is 4, so this will be always 12. We cannot change that. But what we can change is something which is not the output of a function. For example, the 3 here. 3 is an input as well. It has no connected functions. Okay, so it will be an input of the function, but it will not be an output of the function. So that it's easy for us, it's free for us to change the value of 3. For example, in the formula here, which is might be the model, our model, we can change it from 3 to 3.1 or to any values. So the purpose we decided the value here is that we hope that we can change the value to let the f become 44. Okay, so in here we define the L will be equal to f, okay, minus 44, which is the Guangzhou's here, and the square. Okay, and then so we cannot change the input and Guangzhou's as well. So in this computational graph, the only thing we can change is actually the W here. Okay, so we will call this W as the parameters of our computational graph. So the purpose of for us to do the backpropagation is that we hope that we know the gradient of W, so that we know how we can change the W to change the F, so that the F will be as close to the 44 here as possible. Okay, so let's see how we can do that. So suppose that we want to get the DEL over DW. So as we have repeated for many times, in order to get the DL over DW here, okay, since the W is the input of the multiply function here, so we're just using the F to decompose it, so it will become the DL over DF and DF over DW here. And the F will be VW, the multiplier of V and the W, so that this one will become the V. So it will become the DL over DF multiply V. And the DL over DF, which will be this formula, and it will become this formula. Okay. So in order to decide the value of a DL over DW, we need to start it from here. So the DL over DL to be 1, and we call the backward function of this function block. And the function block know that the differentiation is this one. Okay. And so that we can just decide it. For example, F here is 42, so that's minus 2, so that will be the minus 4V. Okay, minus 4V. And the value of V is 14, we know. Okay, so this is 14, so we can get the value of a DL over DW here by using the backpropagation algorithm to start it from here to here and to here and to here. So we can decide the value of a W DL over DW here. And as we said before, this will be the direction we want to change the W here. Since we need to multiply a learning rate to decide how much you want to change the W. And we know that the learning rate will be a very small number, which we can decide. So that actually the only important thing here, the DL over DW here, we only need to know it's positive or negative. So that we can use Thus, to decide if you want to increase the W or decrease the W. Okay. Okay, so this is how we can using the computational graph and the backpropagation to decide how we can update the parameters here. Okay, since in here we know that the value is negative, so actually we need to increase the W to make the F will be close to the 44 here. So it's obvious because we know that this is 14 multiplied W. So we need to increase this value to make the F become bigger. But actually we cannot increase the W too much. For example, if you increase it to 4, so it will become 60 56. So it will become larger than 44 here. So we cannot increase the W so much. So we need to increase it little by little until the F become the 44. Okay. So this it will be we have discussed how we can use in the computational graph to evaluate the forward path and the backward path. Okay, the forward path is for evaluate the prediction of the model, and the backward path is using to get the gradient of the variable of the parameters in the model, so that we know that how we can change the variable to make the prediction, which the F here, as close as to the ground truth as possible. And this procedure is called gradient descent. But in the previous state, we just discussed most simple situation. Actually, in the computational graph, it's a lot more complex than that. For example, we can have a computational graph with branch. What do you mean has a branch here? Branch means that we will have a variable which is connected to more than one functions here. For example, if we modify the expression to add one term here is a squared here. So it means that a is using here and here is used to both situations. Is to both to two locations here. So the first location is this branch, and the second location here is using this branch. Okay, so if you check the gradients, when we check the value of the A, it will affect the output F via this branch. Okay, but it also can change the value of S via the other branch here. Okay, so A will become here, and the value will actually add of this two will become the 14.007001. Okay, so when we try to decide the gradient, we need to using the 46.007001 instead of 46.001 here. Okay, because this one it depends on this branch only. We need to consider both branches so that the gradient will be a correct value. Okay, so when we want to decide the df of a dA, okay, we need to consider both branch, and actually we need to sum the contribution of the gradient of the both branch here. So it will be since the A will depend on the S will depend on A, and the V will depend on A, so we need to using both variable to decompose the gradient here. So we have two terms, one for each branch. If we have more than two branch, we need to consider all branch here and sum the gradient of every branch to have a true value of the differential gradient of the variable a here. Okay, so this is the easy part. We need to consider both branch. Okay, so when we do the back propagation, but we can do this back propagation to here and increase the change the gradient of the a. And when we do that for the second branch, we need to add the value into the gradient of a here instead of change this one to the gradient. Okay, so this is very important. So whenever we using the upstream gradient to decide the gradient of a variable, we are actually add the contribution to the gradient instead of the set this contribution to a gradient. For example, in here, for the first branch, okay, we decided some value and assign it to the gradient of a. But when we traverse in the second branch to here, we have less gradient here. Okay, we have less gradient here, but we cannot just change the df of the gradient of a to be this value, which will not be incorrect. Actually, we need to add this value into the existing gradient of the functions here. So this is something very important. So that means that before we start the back propagation, we need to clear the gradient of all variables in the computational graph to be 0, so that we can always add it to the gradient instead of replace it. Okay, so let's check a more complex situation. We have a branch here, and this variable with the branch, it is the output of some variable or of some functions. So let's see what it will happen. So suppose we go this branch first to get a gradient of the a. When we traverse the gradient, the path to here, can we just call the backward function to the a here to decide the gradient of the a? Actually, we cannot do that, because if we go through this branch as well, so this time we will have another gradient. Okay, so we can change the gradient here, but if we have a go back to decide the gradient of a here, we cannot call it again, because now we have, because for the a we don't know how we want to change the value here, because because the a will depend on the upstream gradient, which is the gradient of y. It decided is a gradient already, but when we traverse the second branch, the gradient of y is changed. Okay, so it means that the gradient a will become incorrect, so that we cannot decide the gradient of a before the both branch of y are decided, so that we get a real value of the gradient of y here. Okay, so that means that, let's do it again. That means that when we traverse the graph to here, we need to wait for the other branch to be ready. Okay, so that oh, we can we will have a correct value here. So it means that the order of the gradient design assignment is very important. So we cannot just using the depth first. We need to using something more width first, breadth first, traverse algorithm here. And in this situation, actually, we need to decide the visit order of the computational graph. So for example, here, we need to do this two first. And then we do this one, which will be second generation, and this two will be the third generation. And then we'll do in the first generation here, so that now we know the real value of the gradient here, and we do that for this generation to decide the gradient of the A. Okay, so it means that we need to assign a generation for each functions here, so that we know how we can call the backward function of those backward of those functions to calculate the gradient of the input of this function. Okay, but the problem is that how can we know the generation here? How can we know the generation here? Actually, this generation will be assigned in the forward path. Let's see how we can do that. Okay, so the algorithm is that initially when we do the evaluation, we will start it from the input here. So we will have a generation number for every variables and the functions in the computational graph. So initially, this is the input. So we set the generation to be 0 for the A, B, and the C. And then we need to generate the generation. We need to decide the generation of the functions here for this one and this one. How we can do that? The definition, the algorithm is that the generation of a function is the method generation of all inputs. So, for example, here, the square has only one input and the generation is 0. So, the generation of function will be 0 as well. And for this one, it has 2 input. And the generation of both input are 0, so this one will be 0 as well. So this one will be 0. And then the second rule of the algorithm is that the functions, the output of a functions, for the output of functions, for the output variable of the function, its generation will be the generation of the function plus 1. So for example, in this situation, the generation of the x will be 0 plus 1. So it will be 1. And then we can using the whole rule to decide the generation of the whole computational graph. So you can see that the function will be the 1 since that's the only input, and this will become the 2, and this one has 2 inputs, so that we need to we cannot decide its generation for now. We need to wait for the generation of W to be generated. So we need to start it from here to generate a function of this one. This is the maximum value of both, and the U should be 1. And this function, it will be max value of both input, so it will be 1. And this will be 2. And this is 0 since this is the input. So its generation is 0 and 0 and the 2, maximum 0 and 2. This one will be 2. And for this one will be 2 plus 1. So this will be 3. And now we know that this is 2, this is 3. So this will be 3. And this will be 4. So that in this way, we have decided the generation of every functions and the variable in the computational graph. So when we traverse the graph, we can sort all the links via the generation number and call the backward function one by one. So in this way, we will guarantee that the gradient of all variable will be correct, because we have considered, for example, you can see that for this one, for this one, it will be when we decided this functions, the both output has the same generation, so they should have been called already before we decided the gradient of this one. So we call it generation 3, generation 2, generation 1, and the generation 0 here. So the order will be completely correct. Okay, so please try this by yourself to see if you can follow the algorithm to decide the generation of the backpropagation algorithm. Okay, so that's actually the algorithm for the backpropagation. So we will discuss the implementation later for the D0, so that the D0 has implemented this algorithm precisely. And actually, in any deep learning framework like PyTorch or TensorFlow, they all implement the backpropagation in a similar way. And actually, you may ask that how we can decide the generation do the for pass here for this function. Okay, so in the next video, we will discuss how we can using the Python operator override to convert this expression into a function called like this. So we will stop this video here. So if you are interested in how the Python can convert the expression into a function called like this, please check the next video.